Hello. So in the last video we have seen the definition of zero-sum games and the notion of pure strategies and the two quantities max-min and min-max. So in today's video we will see a different kind of strategy where we will randomize over the options of each player. Okay, so let's start with an example of this well-known rock paper scissors game. So there are two players, max and min, and both of them have to choose between rock paper and scissors. So here is the dependency. Now if among the two players, if one chooses rock and one chooses scissors, the person that chose the rock will get a +1 because rock breaks scissors, scissors cuts paper, and paper covers rock. Okay, so this is the payoff for the maximizer. If max chooses rock and min chooses rock, there is a draw, so the payoff is 0. Rock and paper, max gets -1 because paper is better than rock, and rock versus scissors, there is a +1. So similarly you can fill the rest of the cells. Now here let's try to look at what are the max, min, min, max. So what is the max, min over pure strategies? So if max chooses rock, then min can choose paper. If max chooses paper, min can choose scissors, and if max chooses scissors, min can choose rock. So for each strategy of max, min has a strategy which will give -1. So max min pure will be -1. Now what about min max pure? You can see that if min chooses this, max will choose this. If min chooses paper, max will choose this scissors, and min chooses scissors, max will choose rock. Okay, so here min max is +1. Okay, so now consider a different strategy for max. Suppose we say that max plays each choice with 1/3 probability. Okay, so it looks like this. So the strategy is 1/3 rock plus 1/3 paper plus 1/3 scissors. So such a strategy is called a mixed strategy. Here you are mixing over pure strategies, okay, or randomized strategy. Now with this strategy of maximizer, suppose min plays the pure strategy rock. Okay, min is always playing this. Now there is a 1/3 chance that the game has payoff 0, 1/3 chance that the payoff is +1, and 1/3 chance that the payoff is -1. Okay, so this here now we have to talk about an expected payoff. Okay, so the expected payoff will be 1/3 times 0 plus 1/3 1 plus 1/3 -1. Okay, so that will be 0 if min plays rock. Similarly, if min plays paper, you will get the same value. 1/3 -1 plus 1/3 +1 will just give 0. And similarly, if min plays scissors, you will get 0. So this way, so when max plays this mixed strategy and min plays a pure strategy, the expected payoff is 0. So with this sigma and with pure strategies, the payoff is 0. So firstly note that this sigma is better than playing a pure strategy for max, because the max min is -1 over pure strategies. So at least this sigma is better for max. Now min also can play mixed strategies. So okay, so suppose say min plays 1/3 rock plus 1/3 paper plus 1/3 scissors. Okay, so now when max plays sigma and min plays tau, how do we compute the expected payoff? So here is the table. So this is 1/3, this is 1/3, this is 1/3. Similarly, this is 1/3, this is 1/3, and this is 1/3. So this thing comes with 1/9 probability. Okay, so essentially it is 1/9 times this plus this plus this plus this plus, you add all the cells. That will give us the expected payoff. So here it is, and then that will still be 0. Okay, so when max plays sigma, playing a pure strategy already gives 0. So mixing for min does not, at least in this form, does not give any gain for min. Okay, but the purpose of this example was to illustrate the notion of mixed strategies, and when players play mixed strategies, how do we compute the payoff? So you just need to see the probability of hitting each cell and multiply with the corresponding payoff. Okay, so a bit more formally, so here it is, a mixed strategy is a probability distribution over pure strategies. So what are the pure strategies of maximizer? There are choices 1, 2, 3 till m. Then a mixed strategy will be given by a tuple of real numbers, an m tuple of real numbers between 0 and 1, such that the sum of them is 1. Okay. Similarly, minimizer's pure strategies are from 1, 2, 3 till n, and a mixed strategy is given by an n tuple of real numbers such that the sum of them is 1. Okay. So there are infinitely many mixed strategies. Okay. And then given a sigma and a tau, the payoff is given by, so you have to multiply each, so you have to multiply each cell in the payoff mij with the corresponding probability of hitting that cell, which is probability of max playing ith row and min playing the jth column. That will be xi times yj. Okay, so you can write it succinctly as x transpose, so x1, x2, xm multiplied by matrix multiplied by y1 till yn. Okay, now this is for a fixed payoff. Now we are interested in max min and min max over mixed strategies. So max min of m will be defined as the max over all mixed strategies of max and min over all mixed strategies of minimizer, the payoff of the respective strategies. Similarly, min max will be min over all strategies of all mixed strategies of min and max over all mixed strategies of max, the payoff. Okay, so these two are the important quantities of the game which we are interested in. Yeah, so this is what I said. Notice that there are infinitely many mixed strategies. Now the goal is, so now that we know what mixed strategies are, our goal is to compute max min of m given a given a game m. Okay, so last time it was just an enumeration since there were finitely many pure strategies, but now there are infinitely many of them, and here is where we will need some optimization problems. But note that this is a max min, so this does not immediately look like a linear optimization problem since there is a mix of objectives, and moreover look at the cost, the payoff. So x and y are variables, and then this thing is not linear, it contains bilinear terms. Okay, has bilinear terms. So what we will see is that in spite of this, we will be able to reduce the computation of max min to solving an LP. Okay, so this is the goal of this video. So let's start. Okay, so as a first step, suppose we fix a strategy for maximizer. Okay, some x1 to xm are considered to be some constants. For example, in the rock paper scissors game, say that we fixed maximizer strategy to be 1 by third, 1 by third, 1 by third. That's all. We don't perturb it. Now, given this fixed strategy, as a first step, we are interested in finding the best response of the minimizer. Okay, and the best response would be the min over all mixed strategies x transpose my. Okay, note that this is a linear program because these x's are all constant. See, look at this. So we need to we need to look at all mixed strategies of min. So we need to find all y1 till yn such that sigma yi is 1. So each feasible solution of these constraints will give a mixed strategy. And what we want to minimize is this, because here x transpose is fixed. It's a constant, and this will be a linear function over y1 till yn. Okay, so for example, if you look at the rock paper scissors game with x being 1/3, 1/3, 1/3, what is this? Okay, so we want to minimize. So let me show you the picture. So here, instead of 1/3, we should have y1, y2, y3. If I tell you this, then what is the payoff? This will be 1/3 y1 times 0 minus 1/3 y2 times 1 plus 1/3 y3 times 1 and so on, right? So that is what I have written here. So this will be minus 1/3 y2 plus 1/3 y3. Okay, then plus 1/3 y1 minus 1/3 y3. Okay, and similarly you should write the third column, for the third row. Okay, that will be minus 1/3 y1 plus 1/3 y2. Okay, so you can see that this actually sums out to be 0. So for this particular LP, the cost is 0. But anyway, if this was not 1/3, 1/3, 1/3, then there will be a linear function on the y's. That is what we should see here, and that will turn out to be an LP. Okay, so now that we have this, the fourth step is that the answer to the above LP, okay, so which is this LP, gives the best response of min to Max's mixed strategy x1 till xm. Okay, so for each given x1 till xm, we can write this LP and get an optimum value, which is say x0. Okay, now among all the mixed strategies, we want the maximum over all x0s, and that is what will give us the max over min. Okay, so how do we find this maximum possible x0? Okay, so let's first write the dual of this LP. So because this is a minimization problem, and then here we want to maximize x0, our first idea would be to check if we can pose this as a maximization problem. Okay, and for that, let's say we write the dual of this. Okay, so here there is only one constraint, so I have to multiply this with so let me multiply this with a variable called x0. Okay, and then I have to maximize this this thing times x0, which will be just x0. And what are the constraints? See, here there's only one thing. So the coefficient of y1, which is x0, should be compared with the coefficient of y1 in this. Right? Now what will be the coefficient of y1 in this? That will be like, so let me draw it here. So here is the matrix. The coefficient of y1 will be whatever is here times x1 plus whatever is here times x2 and so on, whatever is here times xm. And what is that? That is m1 1 times x1 plus m2 1 times x2 till m1 times xm. Okay, and here you will have a less than or equal to, because see, we have to write this as a, see, this is in which form? This is of the form minimize something with A transpose y equal to C, y bigger than or equal to 0. So this will be transpose y. So this is of this form, and the dual of this would be max of C transpose x subject to Ax less than or equal to B. Right? That is how it will look like. So here the C, there's only one thing. So we wrote maximize x0. Now the coefficient of this should be compared with the coefficient of this with a less than or equal to sign. Okay, that will be the dual. So the dual will take this form. Okay, so coefficient of y2, which will be x0, will be less than or equal to coefficient of y2 here will be m12 times x1 plus m22 times x2 till m2 times xm. Okay, so I have written y1, y2 for each of the n variables. We have one constraint like this. Okay, so this is the dual. So we can write it in this way. So the matrix here, see here the A transpose was 1, 1, 1, 1, 1. So the A is actually an n cross 1 matrix, column matrix. So this times x0 is less than or equal to, this is m transpose x. Okay, so this is the dual of this. So fortunately we have a maximization problem. Okay, now firstly note that primal is bounded. This thing is bounded. Why? Because the feasible region is bounded. Okay, the feasible region is in fact contained inside the unit hypercube. Hence, the primal will have an optimum and the dual will have an optimum, and both these optima will coincide. Okay, so the x0 that we wanted here will be actually the solution to this maximization problem. So this is the main point. For a given strategy in maths, the payoff obtained when min plays a best response is given by the optimum cost of this LP. Okay, so once again remember that we are still in the case where x1 till xm are constants and x0 is the only variable, and given this, solving this will give us the answer for x0. But now what do we want? We also want to make these x1 till xm's as variables, and we want to find the over all mixed strategies, we want to maximize x0, and that is what is the final step. So we want to maximize the optimum of the dual LP with respect to all mixed strategies of the maximizer. Okay, and the only thing left is to consider these things x1 till xm as variables and add these two constraints, which is the fact that this is a probability distribution. The variables are the solutions of a probability distribution, and still you want to maximize x0. And this will give us the LP for computing the max min. So here we have crucially used the dual and changed the min problem to a max problem. Okay, and we wrote it as an LP. Now if we want to write this for the RPS example, the rock paper scissors, so what is this? x0 should be less than, you have to go through this column, right? So x1 times this plus x2 times this plus x3 times this. So x0 should be less than this. x0 also should be less than the corresponding thing from here, and x0 should be less than the corresponding thing from here. x1 times 1 minus x2 times 1 and 0 here. Okay, and then we want to maximize x0 subject to these constraints. So this gives us the LP for computing the max min on the RPS example. So for given a game, we should be able to now write an LP for the max min. Okay, So this is the end of today's video. So similarly, we should also be able to write what is min max, an LP for min max, and then in the next video we will see how to compare max min and min max over mixed strategies.